Let's pretend for a second you're looking for a treasure on this deserted island, and here's your treasure map. You can see that the treasure is right here because X marks the spot. When you're looking for a treasure, you're probably going to have a compass, right? So you got your compass sitting on top of this map, your lamp over here to the side, right? Here's your compass. It's pointing this way. Okay, so you're figuring out, all right, if I walk 27 paces this way and then I turn, and you're figuring this out because you've got your compass there, right? But then it starts getting a little bit dark and you flip on the light switch and all of a sudden you notice, wait a sec, when I flipped on the light switch, the compass needle doesn't point this way anymore. The compass needle points this way. What just happened? Well, you flip off the light switch and the compass needle goes back to the way that it was pointing before. It's getting a little dark, so it's getting a little hard to see, but you can see that when you flip on the light switch, it goes this way, and when you flip off the light switch, it goes back to pointing this way. You start trying to figure out what's going on here. Kind of like when you touch a fridge and a stove, you try to figure out what's going on. It takes you a little while to figure it out. And at some point you realize, well, it points this way every single time the light switch is off, but it points that way every single time the light switch is on. What's the difference here? Well, an electric current. There's an electric current flowing through the wire. Oh, wait, the wire happens to be underneath my map. Maybe the wire is causing this compass needle to be affected. But wait, the compass needle is only going to be affected by a magnetic field, not an electric current. So it's not an electric current that's the issue here. It's a magnetic field that's the issue. But what could possibly cause the magnetic field? There's only one logical conclusion that we can draw from that. It must be the electric current that's going through the wire that's generating a magnetic field. Electric currents don't affect the compass needle. Magnetic fields affect the compass needle. But we must have a magnetic field there when the electric current is turned on that wasn't there when the current was turned off. So the conclusion must be that the electric current generates a magnetic field. In 1819, almost 200 years ago, we're coming up on the 200th anniversary of this discovery, a guy named Hans Christian Oersted made a discovery that is what I would argue maybe the most important technological discovery in history of the world. I wouldn't say necessarily the most important scientific discovery. You know the difference between science and technology, right? Science is pure. Technology is applied. Okay? This is applied. This is applied to almost everything we have today. This idea that electricity generates magnetism. You're looking at an image on a screen right now that's caused by a projector which uses the principle of electricity generating magnetism. When you have your phone in your pocket and you feel that phone vibrating because there's a text message or somebody Snapchats you or whatever, that uses in many places the principle of electricity generating magnetism, among other things, right? But certainly that principle. When you drive your car to school, that uses the principle of electricity generating magnetism in many places. When you listen to Mrs. Stafachuk on the morning announcements, that uses the principle of electricity generating magnetism. When you're listening to your music on your headphones, it uses the principle of electricity generating magnetism. This discovery was made almost 80 years before we even knew that an electron existed. Like, we didn't even know much about electricity, but yet Oersted discovers the relationship between electricity and magnetism, and that is that electricity generates magnetism. Now, Oersted was a pretty smart guy, right? He makes this discovery that electricity generates magnetism, moving charges generate magnetism, but he also figures out what the magnetic field looks like. We know what the magnetic field looks like surrounding a bar magnet. We already knew this. If you have a north pole and a south pole, the magnetic field is going to look like this. It goes away from the north toward the south. That is outside of the magnet. You guys know that inside the magnet, it actually goes the other way around from south to north. It follows the direction of the domains. This isn't new. Okay, this has nothing to do with electricity generating magnetism. What does the magnetic field look like surrounding a moving charge? Well, first of all, let me give you a couple of new symbols that I can that I can show you that help you to understand the direction of the moving charge. And then we'll talk about the magnetic field that surrounds that moving charge. Clearly, if a charge is moving downwards, then we would represent it by that symbol. If it's moving upwards, by this symbol, to the right, to the left, and so on. But what if it's moving this way, away from you guys, into the page, away from you guys? What if it's moving this way, out of the page, towards you guys? It's a little bit harder to give you a symbol for that. Well, I'm going to tell you that the symbol for out of the page is a dot. The symbol for into the page is an X. Now, the magnetic field surrounding both of these, the particle coming out of the page, as represented by the dot, is circular. Going into the page, it's also circular. But the reality is, it's not actually just one circle, just like when I draw the magnetic field up here, it's not just really one field line, it's a number of field lines. And we've got a series of concentric circles surrounding the moving charge. And those concentric circles get further apart from each other. Looks like this. That's the shape of the magnetic field. The magnetic field is circular. But what's the direction? We define the direction surrounding a bar magnet as being away from the north toward the south, the way that a compass needle would point when placed in the field. Well, if you put a compass needle right here, it would move in the direction of the field as well. But which way is that? We're going to use a rule called the wire grasp rule to figure this out. Here's what I want you to do right now. I want you to take your hands, both your hands, put your pens down. And I want you to do this, please. Put your left hand in. Put your left hand out. Put your left hand in. And shake it all about. Now do that. No, never mind. The reason that I want you to get your hands all limber here is because you're going to use a rule called the wire grasp rule to figure out the direction of the magnetic field caused by these moving charges here. Okay, here's how it's going to work. The wire grasp rule says you're going to stick your thumb in the direction of the moving charge. So in this case, case number one, your thumb is going to go out of the page. So that's towards you guys, towards the back of the room. Okay, that's the way you stick your thumb. In this case, you would stick your thumb into the page, away from you guys, towards the front of the room. Got it? Your fingers, you're going to bend. It doesn't matter how much you bend them. Okay? Maybe somebody bends them like this. Maybe somebody bends them like this. Maybe somebody just scrunches them right up. Doesn't matter. Okay, bend your fingers. Your bent fingers will point in the direction of the magnetic field. But wait. Why doesn't it matter how much we bend the fingers? Because that clearly changes the direction my fingertips are pointing. Well, look. If I do it this way and bend them just a little bit like this, my magnetic field points this way. If I bend them a little bit more, which way are my fingertips pointing now? You're always looking at the tips of your fingers. Which way are they pointing now? Oh, look, they're pointing down. What if I bend them even more? Now they're pointing to the left. What do you notice about that magnetic field? We say it's going clockwise. It's a full loop going clockwise around there. Similarly, if we look at this one, we'd say thumb into the page, fingers go, well, here it's left, here it's down, here it's to the right, here it's up. It's going to go counterclockwise. Does that make sense?